Well, hello, everybody. If you don't know me, I'm Michael Scharf. I'm the co-dean of Case Western Reserve University School of Law. We are one of the two partner schools, along with Western Ontario, that make up the Canada-US Law Institute. And you're going to meet today several of the people whose time and energy is well spent putting together this conference and the other activities of the center. It is a great pleasure to welcome you to a spring day in Cleveland as we look out the window and see the snow falling here in the beautiful botanical garden. And one of the things I do tell students when I'm recruiting from Arizona and California to come to Cleveland, I say, you know, in Cleveland when it's cold, we just cross the street and we go to Costa Rica. And that's because the botanical garden has a giant Costa Rica biosphere. And you are invited today. The building is completely closed off except for you. And you all are invited at any time to explore the Madagascar spiny desert, the Costa Rica biosphere, and the theme that they're building today is butterflies. And you'll see many butterflies in there. Now, butterflies are not going to exist much longer if international global climate change it continues unabated. And that's the real reason we're all here at the conference today, to talk about what the two countries, Canada and the United States, can do to try to hold off climate change and to respond to its ravaging effects in both countries and around the world. We have an amazing panel set up for you today. It's going to be a fantastic conference. And one of the most important things about this conference is the ability for people to network, to get to know each other. You get to know Canadians, Americans, business people, government people, academics. We're all here sharing one experience. So without further ado, I will ring Henry King's famous bell that has been rung for 43 years at the start of every Canada-US Law Institute conference and call the conference to order. Okay, let me now turn things over, thank you. Let me turn things over to Steve Petrus.
Thank you, Stephen. Yeah. Thank you, Michael. Thanks for opening our 43rd annual conference of the Canada-United States Law Institute. Welcome everyone here to the Botanical Gardens. Perfect setting for a topic on climate change, a discussion on climate change. So what we're going to do, we're going to get right into the program now. At our luncheon program, we're going to have an introduction of our executive committee and of the other people who make the Canada-US Law Institute work. But right now, we're going to jump right into the program. So in putting together this conference, we thought it would be very important to set the stage with the science, you know, with the facts. What are we talking about? What is climate change really? What's physically going to happen in the United States and Canada that we need to deal with? So we looked around to find who's the right person who can tell us about this. And we actually hit an absolute grand slam home run because we have with us today Dr. Eugene Tackley. He is the Emeritus Professor of Agronomy in the Department of Geology and Atmospheric Science at Iowa State University. He's an undergraduate in physics, and he's also a PhD in physics. And then he started focusing in on climatology. And interestingly enough, he is the founding member of the multi-institutional, multinational team that has assessed the future of climates in the United States and in Canada. And he did this together with Iowa State, a number of other institutions, including the University of Quebec in Montreal. Okay, interestingly enough, all of you have probably heard about the 2018 National Climate Assessment, which is published by the U.S. government as a statement about the situation and facts of the climate. It was a very infamous document this past year because our present administration didn't like it that much, was very critical. Well, Dr. Eugene Tackley is one of the co-authors of that study. So he's not only a person who has assessed the impact of climate change on Canada and the United States, he organized the teams to do this investigation, and he's also an author of that national study and statement on the climate of the United States and Canada. So without further ado, Dr. Tackley, the conference is yours.
Appreciate those kind words. So we're going to jump right into the background here. I wanted to give, not be presumptuous that you have studied this. You've probably seen fragments of this, but I'm trying to pull this together, the core of why we understand climate change and the significance of this. So I'm going to be going in two sections here. We'll look first of all at the fundamental science, and then we'll look at some of the issues and impacts so that we can look at some of the factors that are going to be driving the impacts and the things that we have to think about trying to develop resilience to, because some of these are going to be very serious, and we'll get into that. We have a lot of good foundational documents to draw on to look at both the science and the impact. So, for instance, the Intergovernmental Panel on Climate Change issues about every 5 years a state of the climate on the global scale and an update on the science of climate change. And so we have the 2004 issue of that. And then we have national documents that parallel the international document. The one for Canada is put out by Natural Resources Canada. And so that's an updated document that you have at your disposal. In the U.S., we have two documents. One that was issued about a year ago, which covers the science of climate change. So it takes the IPCC document and then updates it and focuses on the science for the U.S. And then the one which is just issued the day after Thanksgiving was the fourth national U.S. climate change assessment, and I was involved in that one as well. So we'll look at some of the fundamentals of why we have this issue, and then we will look first globally, and then we'll look at North America and just a few words about the Great Lakes. Well, the climate system, when we talk about the climate system, we're really talking about land, oceans, atmosphere, and ice masses. Those are the four components of the climate system. And energy moves between these and among these reservoirs then. And so to understand the climate system, we have to understand how energy and mass is moved among these reservoirs. So ice melts, and it takes energy to melt ice. So part of this increase in energy that we're seeing is used to melt ice. And so that's the way we look at it. We use the laws of physics, the same laws of physics that we use to build airplanes, to build nuclear power plants. We have confidence in these laws because we ride in airplanes with confidence. We can live in the vicinity of nuclear power plants because we know we've used the laws of physics to design these. These same laws are used to look at our climate. Now, there's a lot of uncertainty because the climate system is a big system, and we need a lot of observation. So there's a level of uncertainty, which is also a part of our science, to quantify our level of confidence in these various statements that we make. And so when you read these documents, you'll see references to how confident we are in the results. Well, there's 10 indicators, or at least 10, that we can look at then. So it isn't just warming of the globe, but it's sea surface temperatures, it's sea level, it's water vapor in the atmosphere, which is going up in a warmer world. The near surface, the lowest 2 or 3 miles of the atmosphere, we look at the temperatures of that. We look at glaciers that are melting, snow cover is going down, sea ice is going down. We look at temperature over land, and a very important one is ocean heat content, which hasn't been given much attention, but 90% of the heat that comes into the climate system goes into our oceans. So that's a reservoir that's sitting there waiting and could be redistributed in ways that we are only beginning to understand. So that's an important factor of the climate system. So the basic concept is then that the greenhouse effect is a natural effect, and we're glad we have that because that's what keeps us from having a global average temperature of about minus 10 degrees Celsius or something like that. So it has a blanket of these gases, mainly carbon dioxide, but also nitrous oxide and methane, that trap some of the heat and keep it from going back out to outer space, and so it's redirected toward the Earth. Now what we're doing is we have increased the levels of carbon dioxide, methane, nitrous oxide, and a handful of other gases to the point where more of this solar radiation is being trapped. And that means that the temperatures in this vicinity are rather small. Now, it's always important for me to point out that this cartoon here shows that we have this big, thick layer here. In fact, if the Earth was the size of a basketball, this layer would be the thickness of 2 sheets of paper. That's all it is. And it's that thin sheet, and there are 2 gases, there's carbon dioxide and there's ozone. If it weren't for those gases, in that thin sheet of atmosphere, we couldn't survive. Plants, animals, people could not survive. Lack of ozone means that the ultraviolet light would fry us. And carbon dioxide, not having the right amount of carbon dioxide, means that the terrestrial biosphere as we know it could not exist. So this very thin sheet of atmosphere is what we're doing a gigantic chemistry experiment on. And we don't know the outcome. So that's the sobering reality of it. So if we look at carbon dioxide, which I'm going to focus on carbon dioxide, but we'll make a little bit of, talk a little bit about the others. But carbon dioxide, if we look at the record, and it's hard to see from where you're at, but this is an 800,000 year record. So it goes back 800,000 years, and this is the present. And you can see that over that time period, carbon dioxide has never gone above the blue line. Blue line is 300 parts per million. And so at about 1900, with the Industrial Revolution having begun 120 years earlier, we've introduced a lot more carbon dioxide in the atmosphere, so it went up to about 300 parts per million. Well, about a year ago, we finally got up to 400 parts per million, so we've increased the carbon dioxide, this key gas that regulates the heat of our planet, the temperature of our planet, we've raised it by over 30 to 35%. And it's going up. There's no sign that it's going down anytime soon here. So we're now up here at about 400 parts per million. So here's a sort of an iconic figure that's often used to show how the temperature of the planet has changed, in this case from 1880 to 2018. So we can see that there's been variability from year to year, but then starting in about 1970, we started on this upward trend, a very monotonic upward trend with fluctuations year to year, even decades. There'll be decadal averages that maybe haven't gone up quite as much as some decades as others, but generally an upward rise. And with our modeling studies, we know that it's these greenhouse gases, the increase in these greenhouse gases, that are the cause of this rise that we're seeing now. Well, we can say, well, maybe it's natural variability. Well, let's look at natural variability. There's the impact of volcanoes. In the last 60 years, we've had 3 major volcanoes. We have Mount Agung, 1963, El Chichon in Mexico, in 1983, and Mount Pinatubo in the Philippines in 91. And you can see every time we have a volcano, we see a drop in the global average temperature by about 1 or 2 degrees Celsius. It drops, and then it gradually comes back over a period of about 2 years back to whatever the pre-existing trend was. So it has a temporary effect by putting lots of particles in the atmosphere that reflect more solar radiation. So it forms a kind of a shield or a reflective area, but it's transient, and it does not have a long-term effect. But it's important nevertheless. We also have El Nino events, or we call them ENSO, E-N-S-O, which I've referred to down here, which the El Nino and La Nina combination. El Nino event is where the tropical Pacific Ocean, for reasons that are not fully understood, goes through a warming period, which may last for a few months to maybe even a year. And during that period, this extra warming we get in the tropical Pacific has a global impact. It causes the temperature to rise. And so we see every time we have an El Nino, we see a spike. It may last just a year. It may last even a little bit longer than a year. I should point out I haven't listed all the El Ninos. I've just listed some that demonstrate what a strong El Nino can do. But nevertheless, that's part of the natural variability. Now, if we also look at the La Nina, which is the opposite effect, that is a cooling in the central Pacific, it also has a global effect. And so you see that when, for the blue arrows, every time there's a blue arrow, you see there's a decrease in the global average temperature. Again, for maybe a few months, maybe for a year. So this then gives us a measure of some of the natural variability, because a lot of the climate skeptics say, well, it's just natural variability. Yeah, we have natural variability, but look at the scale of natural variability versus the scale of the greenhouse gas, extra greenhouse gases that we've introduced. So the science is clear. We know thermodynamics well enough that if you put heat into a system, the temperature goes up. And so that's what we're doing, and that's what we're studying here, and these are the consequences that we have. So we have to conclude then that there is really no known natural phenomena that's influencing a global and regional climate on scales of a century that is as large as the human influence caused by the emission of these greenhouse gases. I'm going to talk mostly about carbon dioxide, but just let me say a word about methane. Methane is about 20 times as potent as CO2, but its concentration is much lower, about 1,000 times lower. However, it has a short lifetime. So if we're making policy, one of the low-hanging fruit areas is reduction of methane. So that might be something to think about. The sources of methane, anthropogenic sources, are from ruminant animals, enteric fermentation in animals, cattle, dairy cattle, goats, beef cattle primarily. Also from natural sources of wetlands, landfills, rice cultivation. These are sources of methane. And we have some, and are doing some work on that. Diets of ruminant animals can be twiddled to reduce amount of methane produced and so on. Nitrous oxide is a very potent greenhouse gas, about 200 times as potent as carbon dioxide, but it's in, again, even much lower concentration, but it results from agricultural activities and some other sources that could be addressed also, should be addressed as we look at all options for reducing greenhouse gases. Well, let's look at the consequences. This is the observed surface temperature, 2001 to 2012. We don't have data over the polar regions over that region of time, but you can see that the warm spots are primarily in the northern hemisphere, high latitudes, and in some areas in South America. But so we have good evidence that the planet is warming. Only a few regions that actually cooled over that period of time, and we know pretty well why those are occurring as well. Precipitation over land, same period basically, or actually two periods here. If we look at the whole period of 110 years, you can see there's been precipitation increases as would be expected in a warming climate. If you have more heat, you're going to evaporate more water, you're going to have more humidity in the atmosphere, you're going to get more rainfall. So you just speed up the hydrological cycle. You can see that it's been intensified and polarized more in the last 50 years. We've seen that the eastern half of the U.S. or eastern half of North America has seen increases, as have the northern parts of Europe, but also the dry areas have gotten drier. So again, kind of a warning sign, a heads up that some of the extremes, the wet regions get wetter, the dry regions are getting drier, and we have to look at populations that are influenced by these regional changes. Other changes that have been observed: snow cover, spring snow cover in the northern hemisphere is going down. Arctic sea ice, we'll come back to that. That's also going down dramatically. We'll come back to this one also. Ocean heat content is going up. As I mentioned, a lot of the heat that's coming from this trapping of by greenhouse gases goes into the oceans. And sea level is rising, and we'll come back to that. So let's look at ocean heat content. These are huge numbers now. This is 10 to the 21st joules, or 1 zeta-joule. That's a new one. We've gone from megabytes to terabytes to exabytes and petabytes, and if you go up a couple more, you get to zettabytes. Well, this is zeta-joules. But at any rate, you can see that both the upper ocean, the lowest, or the upper 2,300 feet, is warming quite rapidly, went up abruptly at the beginning of the 21st century. But also now the deep ocean is getting involved, and so heat is being distributed through the ocean, and we don't really know what the consequences of this continued warming of the ocean are. We're certainly going to change the overturning. One of the worries is that we might slow down some of the global ocean circulation that moves warm air from or warm water from the tropics to the polar regions. So we may have some changes in the Gulf Stream, for instance, which is a major source of moving heat from the tropics to the poles. Northern Hemisphere sea ice, our observation period here maps onto the satellite period. So we can see that there's a substantial drop in Arctic sea ice, which is continuing, and we'll see a projection of that in just a minute. Looking at Canada, now these are a bit washed out, but these are observations in Canada. So this is temperature. So these are the prairie provinces here, the Arctic up here. And you see that there's been substantial warming in the west. And so you can see it gives you kind of a heads up about forest fires and so on, drying in that region. Also some warming in the southern prairie provinces. Overall, average mean temperature has gone up substantially in the last 60 years. If we look at precipitation, we also see that coastal areas have had precipitation increases, and so some of the flooding that's been seen there in Alberta here has had some major flooding in recent years. Overall, again, a rise in precipitation over Canada, and this Arctic sea ice plot shows both the summer demise of sea ice, but also even in the winter, in March, the end of the cold season, you can see that even the extent of ice has gone down during that period. Great Lakes, of course, are the Earth's largest freshwater body with about 20% of the freshwater surface area. Certainly plays a role in the economy of the Midwest for shipping, industry, water supplies, fishing, recreation, and so on. But it's under siege now because of stress from pollution, nutrients, addition, and sediments from agricultural systems, and also invasive species are becoming more of a problem as we move forward. Let's move into future climates. So if we're talking about future climates, first of all, we have to consider that it's going to depend on what our emissions of greenhouse gases are going to be in the future. Are we going to adopt a really good renewable energy future that reduces the amount of fossil fuels we burn? Are we just going to do business as usual? If we do business as usual, we follow this red curve here. This is, and we'll see this RCP, these radiation constructed pathways that can go from a very low emission of carbon dioxide and other greenhouse gases to a very high. So 2.6 is low, 8.5 is high. You'll see that referenced in some of the scenarios that I've plotted here. So if we go ahead and continue this, then we can expect a global average temperature rise of between 4.5 and 5 degrees Celsius, way beyond where we've been with temperatures on the planet in the last many centuries. If we adopt say a 4.5 scenario, that's the blue, then we would be able to keep it down to about 2.5. But And the agreement that was reached in Copenhagen in, I can't remember the year now, but there was an estimate to what would be a guardrail that we could set, and that was that we would not have major impact on water supplies, agriculture systems, natural systems, and that was estimated to be 2 degrees Celsius. Well, we don't have much headspace even now. So if we're going to keep the planet from more than has been estimated to cause major interference with the natural climate system, we have to get on with this battle to reduce greenhouse gases. So let's look at some scenarios. These are from the IPCC report. So here's a low output scenario. Here's a high emission scenario. You can see that generally, this is temperature, we're seeing that the Arctic regions are going to warm much more than average on the scale upwards of 9 or 10 degrees Celsius. Very large rise, enormous impact on ice masses. And if we start to warm and start to melt Greenland, we could go into an irreversible condition there that leads to melting of Greenland over several centuries. A very worrisome scenario. Precipitation, we see that precipitation is likely to increase primarily. This is percent-wise now, so if it's small and you double it, then it doesn't lead to a big increase in absolute amount, but big increase in percentage-wise. But however, it does have a big impact on the polar regions, and also some tropical regions that would likely be impacted strongly. This is sea level, and sea level rise generally would be expected to be in the order of close to a meter, a little bit less than a meter. If we look at some other factors, also again from the IPCC. By the way, if you're looking, if you get a copy of this, and I'll give you a copy of it, or you get it from the conference organizers, the citations are all listed here, so you know where they come from. If it's not listed, then it's something that I created. But here is then the 2 pathways that if we follow this 2.6, RCP 2.6, you see that we can make this temperature level out by the end of the century. However, if we go business as usual, we'll be up in this 4 degrees Celsius range. If we look at sea ice extent, the only way we can keep sea ice from disappearing in the summer is to adopt this very efficient strategy of low carbon emissions in our future. Otherwise, we're going to lose our Arctic sea ice by 2060 or 2070. pH, ocean acidity, is often overlooked, but has become a very important factor too now, because some of this carbon dioxide is dissolved in seawater. And so it raises the acidity, or it lowers the pH of seawater. And that's we're already seeing that the warming and the acidification of the oceans is having impact on coral reefs. Very sensitive structures in our oceans that lead to a lot of very rich and diverse ecosystems in shallow coastal areas, but they are already being affected. So here are some simulations looking at the pace of climate change, and these are simulations by the Canadian Center for Climate Modeling and Analysis. And I want to point out that we have very, very good working relationships in the scientific community between Canada and U.S. And these go back a long ways. My own group at Iowa State, we've worked with the Canadians at Uranus. Michael might be saying, or Mark might be saying a little bit more about this afternoon, but a team that works directly with stakeholders to say, what is it that you need and what kind of climate products can we generate to help you make those decisions? Very good people to work with. We worked with them back in the late 1990s. And but this was not from Uranus, this was from the Climate Modeling and Analysis Center, but it shows you the trend, and you see how the warming starts in the Arctic regions and progresses down, just works its way down through the whole continent. If you go on this website, it's listed here, you'll actually get this as an animation. So you can just, it marches through year by year, and you can just watch it progress. It gives you better insight into how and where these are going to be. That's 3 minutes? Okay, we'll go big time here. Okay, precipitation. These are from our U.S. My group that I work with in the U.S. showing precipitation changes that are expected by end of century. This is a high emission scenario, but you see, again, precipitation projected to increase pretty substantially in the Arctic area, but also we're seeing continental drying in the summer. That's going to be problematic for, particularly toward the end of the century with regard to agriculture, and we've looked at this in the Midwest. Let's look at some other impacts of, for instance, heat. Projections are with a high emission scenario that some regions of our country are going to see on average over 120 days with temperatures above 100 degrees Celsius, 100 degrees Fahrenheit. That's when you consider water supplies for Las Vegas and Phoenix. You have to consider that this is what they're going to have to provide. This is what the outdoor environment is going to be. Pretty sobering. If we look at one of my colleagues at Iowa State, Craig Anderson, has looked at heat and violence, particularly assaults and murders. Now, he separates those from nonviolent, car thefts and petty theft and so on. Assaults and murders scale upward with temperature increases, a very distinct. Looked at many populations. There's an increase in violence with temperature. There is no increase in non-violent crime, but there is with violent crime. So that's something we have to consider, particularly as we move forward and we find that some of our heat waves, 5-day heat waves, are going to be much larger. This is something we looked at in the 2018 climate assessment of the impact of heat waves. I don't have time to talk about that now, but sea level rise, we could be seeing on the order of a meter rise in sea level by the end of the century. A meter rise in sea level would take out these areas, would inundate these areas in red, so we'd lose the Keys, we'd lose Cape Canaveral. Many of the favorite cities here in the winter would be inundated, so we have some real challenges. Miami is already looking into their problems with sea level rise. The military has $100 billion at risk, naval facilities only, for a rise of sea level of 3 feet, 1 meter. So the military has a big relocation problem on their hands. This is something we better start planning for now. This is the kind of thing that we get. This is Iowa. This is not the current year. We're seeing a flood now of this size in progress right as we speak. It's estimated already to be over $1 billion in damage just this week. Here, noteworthy is this is an Iowa town downstream of Cedar Rapids. Here's a hog confinement facility. Here are grain storage facilities. So it isn't just people that's at risk, it's our storage, it's our food supply, it's animals that are under confinement that multiply the effects of these events, which now are at historic levels. Great Lakes, what's going to happen there? Well, what we observed so far is there's lower ice cover in winter, warmer summers, more frequent, more intense storms. Water levels are influenced by warmer air temperatures and drought and changes in precipitation pattern. Also, very important is that these, as the warming progresses, it changes the cycling of the water, and so it changes the transport of nutrients from deep water to the surface, and so that has a profound effect on ecosystems. There is a natural cycle, an annual cycle of about a foot or so, and the historic highs and lows are about a 5-foot difference. If we look at projections for the future, we could see about a 6 to 7 degrees Celsius rise in surface temperature by 2100. They will fluctuate at a lower level, probably more widely around a lower mean. And there will be a decrease in the ice mass. If we look at some of the economic and social disruption that we've already seen, and this is the 21st century, so these are all since 2000. This is Canada. You can see here they had a $1 billion flooding event in Alberta in 2013, and others, primarily hurricanes, tornadoes, flooding, wildfire, and windstorms. If we go to the US, we see the same thing. This is just 2018 alone, 1 year, $14 billion in economic damage. Wildfires, flooding, we have drought, tornadoes, storms, hurricanes. And so if we look at the changes that we've seen here, this is 1980 to 2018, the big ones up here in the 12 to 16 billion dollars have all been since the year 2000. So we're in a different realm. We've got to start planning for this. We've got to develop resilience policies that will enable us to avoid this kind of economic disaster. So, and finally, my last slide here is climate change hotspots. This is some work done by our colleague Filippo Giorgi in Italy, looking at regions around the globe which, according to this regional climate change index he has developed, where a big red spot, it means that there's a big climate change. And it's important to recognize that our societal structures are all tuned to the local climate that we've had during the 20th century. The rainfall patterns, the temperature patterns, the seasonality, and so on. Now those are all changing, which means that the agriculture that we've finely tuned for a particular area is going to have to change. You raise soybeans in Iowa, in the central part of Iowa, you take those soybeans and put them in Minnesota, they won't grow well. They won't produce because it's been so finely tuned for that specific location. You can find your other favorite structure of society that also is very finely tuned. So we've got to start thinking, and just pointed out that what's going to happen then when we have people in these high impacted areas, what are they going to do if their food supply is being threatened? Or as was the case in Syria, 2 year back-to-back droughts led to people migrating to cities, overwhelming city services, and leading to unrest and terrorism and so on. So in summary, the science is clear. Climate change is real. It's already here. It's having a negative impact on our society, both of our countries. There are some aspects of climate change that we're taking a benefit from, and that's good, but they're not going to last. The projections of future climate scenarios point to costly impacts on infrastructure, forest and agriculture productivity, human health, and societal instability. Thank you very much for allowing me to come and participate.
Thank you very much, Gene, for that very interesting report. Does anybody want me to turn the heat up in this room right now? No? We have time for, let's say, 2 questions for Dr. Tackley.
Third question, I have a microphone. Bring right over. Sorry.
Okay, right here. Peter McKay.
Thank you very much, Doctor. Fascinating presentation.
Thank you.
One of the things that you said that struck me as quite stark was this increase in violence. And clearly you have the data that shows this, but can you unpack that a little further and attribute why that is having that particular outcome?
Yeah, Craig Anderson, a colleague at Iowa State, has done this. It's a paper published this present year, just a couple of months ago. He shared some of this information with me. The early, now he has just used annual temperature. But we need to do now is we need to look at heat waves, specific heat waves, because we know that it's a 5-day period, or it's day after day. That's what really gets to people. You can usually take one really hot day, but it's these extended periods. And so what they've done is they've looked at various cities, and they have made the corrections for demographics, for different factors that you would say, well, people are just more outside in the summertime, but they've made corrections for that, and they've teased out the climate-only factor. I'm not an expert on that, but I can point you to the literature. I can help you to work with that. Thanks, Peter. Good question.
More question?
Oh.
Terry Fitzpatrick.
Got a couple here.
Dr. Techley, I'm not sure if you've ever heard of a book by an author by the name of Tom Nichols called The Death of Expertise. He's a professor, I think, at the Naval Academy. But he talks about the skepticism in our society of experts, and the fact that the irony of the fact that with all of the different means we have to get information now through the internet, that people are actually becoming very much in their silos, just getting things that sort of confirm maybe the biases that they have. I was just wondering if someone like you has any ideas how the scientific community can communicate, or policymakers can communicate more effectively with people to try to get the facts out there to overcome some of the skepticism that we have.
Yeah, that's a question we've done a lot of hand-wringing in the climate science community. We recognize that we dropped the ball early. We were not communicating early, and we were too focusing on our own research. But the facts, people will, when you present facts to people, they will back off and they will go to further and further away kinds of arguments. So it basically then comes down to what's my own personal beliefs. It could be based in religion, that the God that I believe in wouldn't let this happen to us. So but we can't do scientific research on that. That's not something that's fact checkable. So then we're kind of left there, that they're presented with all the facts and they're not going to do it. We're seeing this with vaccinations. We're seeing it with pasteurized milk. You know, it's just a part of the society we live in, that experts and science is not held in high value the way it used to be.
Thank you very much, Dr. Techley.